This is our second converting video where we're going to take a look at converting parametric equations to rectangular equations. So we're always going to start out with a set of equations. And I am going to talk through the steps that are written on the side, so you will have time to write them. Now the calculator also gives the option, and you can do this too, you can use a capital T instead of a lowercase t. So you'll see when we go to graph and use the calculator that the capital T will show up as an option for the parametric, and you might find that easier to write and recognize than the lowercase t. So the key here is going to be a substitution. We want to eliminate the parameter or eliminate t. So our first step in order to eliminate is we're going to pick one of the equations and solve for t. So this will eliminate the parameter. So what makes it the parametric equation is it has that extra variable. I always pick the equation that's easier to solve for. So if I look at my first equation, 3t squared, I'd have to divide by 3 and square root. Whereas if I choose the second one, all I have to do is divide. So I'll divide by 2 here. I get y over 2 is equal to t. And then second step, substitute the result into the other equation for t. So I'll take my result of y over 2, substitute it in for t. This is no different than substitution that you've already done with other algebraic equations. We're just applying it to this new situation. And then we're going to simplify. Oops, I forgot the 3 in the front. We'll simplify this. It would be either 3y squared over 4 or x equals 3/4 y squared. So I wrote you can really solve for either variable, but the cool thing about this type of graphing is we have the option to graph things that are not functions. This would graph a horizontal parabola. It's actually not something you probably saw in your Algebra 2 class. We used to look at this, and we have since cut some things down. But if you think about your y equals parabola faces vertically, your x equals parabola, x is horizontal. But it's not a function. So this would allow us to graph something that's not a function if we were to plug in values from negative infinity to infinity. That won't really make sense until we get into graphing, but that's something to think about, and that we might get some of those types of equations later on. Okay, our second one, I had started this video and then got interrupted in between, so I have some of the work done down below for the second one. I'm going to go with the capital T in this one, but you can continue with the lowercase t if you like that better. I'm just showing you that option. Again, we're going to pick one of our equations to solve for. I'll bring the steps back a little bit. The first equation has 1 step, the second equation has 2. So I'm going to pick my first one. All I have to do is add 3 to both sides. And then I can substitute that in for the t, which I already have highlighted in green, in the other equation. So it'll be 2 times x plus 3 plus 4. All right, and the nice thing about this one is it ends up being a linear function, and since our standard format for a linear function, or one of our standard formats, is slope-intercept form, y equals mx plus b. We're already in a nice format for this, so really no other need to do any more simplifying. Now my next one, going back to the lowercase t. If we were in class, I'd ask for a preference, and usually one person would tell me what they want. So I don't know if that would give me a good representation anyway. This is a little bit different because it's going to be harder to solve for t. If you think back to our exponential unit, in order to get that exponent out of that space or that variable out of the exponent, we would need logarithms. And we don't really want to have to do that here. So you can actually solve for e to the t because they have that in common. So you don't have to just solve for a variable. It's just something that you can use to do your replacing. So we're going to solve for e to the t, then replace the entire e to the t with the result. It really doesn't matter which one we go with. I'm going to go with the first one. There's two, each of them have one step for solving. This is adding. So I'll solve that for e to the t. And then I'm going to take this x plus 3 and replace the entire e to the t in the other equation. So same concept of substitution, except we're not fully solving for a variable. And then this one, although it looked complicated to start with, also ends up coming out to be linear. So we can keep it in that y equals mx plus b format. And then the last one is my personal favorite, since we just finished up a unit on this. Let's go back to the capital T. You pick whichever kind of t you like. And this is going to be a little different. Rather than solving for t, we are going to solve for sine and cosine. Just going to write sin and cos, even though I really mean sine and cosine of t. So this one will be x over 3 is equal to sine t, and this will be y over 5 is equal to cosine t. Now we are going to jump back a bunch of units, and we are going to use the Pythagorean identity back from our second unit. And I can already hear some groans from afar. So sine squared t plus cosine squared t is equal to 1, or vice versa, you could do cosine squared plus sine squared. And remember, this is a shorthand notation for sine t squared and cosine t squared. So having the squared as part or attached to the word part of the function is really saying the whole function is being squared. So we are going to substitute in the x over 3 for sine t, and then we're going to substitute in the y over 5 for cosine t. I'm going to use parentheses like I do every time I do my substituting. And then we'll simplify, and we get a very, hopefully, very familiar equation, x squared over 9 plus y squared over 25 equals 1. This comes from the unit we were just in. This is the equation of an ellipse because it has adding in the middle of it. And when we get into graphing, you will see if you hit the graph button or if you plot the points that you get from the table, you will get an ellipse. It's much harder to graph an ellipse in rectangular form. Very easy to type in 3 sine t and 5 cosine t and get that ellipse equation. And if you think about this would be a vertical one, that's not a function. It's so easy to graph in the parametric format. All right, so that concludes the different types of examples for converting from parametric to rectangular. And now you should be well equipped to start working on some practice of some varying types of these. See.